In this video, we will take a look at another perspective of linear regression and how it can be used to find the output of the logical operators AND, OR, and XOR. While you might not think of the logical operators as methods for regression, we're going to see that the linear regression models we've been using can be used to predict the output of some logical operators. We will then use this as motivation for the structure of a neural network. If you aren't familiar with the concept, a truth table is a table that consists of logical inputs and an output. In the case of the AND logic table that we see on the screen, we have two inputs, x1 and x2, which are used to determine the value of the output y. All permutations of x1 and x2, taking values of 0 and 1, are listed in the table, for a total of 4 lines. The only time that the output value y will be 1 is if both x1 and x2 are equal to 1. This is similar to the concept of an intersection in set theory or probability, where an element is part of the intersection only if it's true that it's in both of the original sets. For the OR logic table, like a union in set theory, the output will be 1 as long as at least one of the input values was equal to 1. The only case where the output is 0 is when both of the input values are 0. Finally, we have the exclusive OR, which in computer science terms, we call this the XOR. An exclusive OR will have an output of 1 when exactly one of the inputs is equal to 1. If the two input values match each other, then the output will be equal to 0. Our goal for this section is to see if we can come up with a linear equation that can be used to categorize the output of each of these logic tables correctly. We can use linear regression to help us create this linear model. We will start by looking at the AND truth table. Suppose that what we see on the screen is a set of coordinates in x1 and x2, and y represents an output category, either 1 or 0. We can graph the values on a coordinate plane where x1 is on the x-axis and x2 is on the y-axis, with y being the color of the point, like you see on the screen now. Can we create a line that will separate these values completely? It appears that we can. This means that we should be able to create a linear equation that can be used to classify values as either 0 or 1, given the inputs for the AND logic. To find our best fitting line, we first need to import the OLS function from the stats model formula API package. Next, we need to define the data for the AND logic table. Note that I'm making a dictionary using x1, x2, and y as the keys, and the appropriate values of zeros and ones are stored as the values within the dictionary. Next, I can create my least squares regression equation predicting y from x1 and x2. Finally, I fit and print the model. As we saw with our linear regression before, this provides us with an intercept term and a slope value for each of our two input variables, x1 and x2. We can use these estimates to help us create an equation for prediction. In particular, if we were to use the predict function on the original AND data, we would get output values of 0.75, 0.25, 0.25, and negative 0.25. This doesn't give us exactly what we're looking for, though. However, as we saw with logistic regression, we can apply a transformation to our data, and it will provide us with specific outputs that we're looking for. Here you can see that I've applied an array round function to my model predictions, and the output that I get now matches the output for the AND logic table. Next, we will work with the OR logic table. Again, we will use the x1 values as our first input and the x2 values as our second input, trying to predict the value of y. Graphing these values, like we did for the AND logic, gives the graph that you see on the screen. These values can also be separated by a single line, which means we will again be able to use regression techniques to predict the output. At this point, try pausing the video to see if you can modify the code from the AND logic regression example to implement the OR logic regression example. What values do you get for your outputs? Do you need to apply a transformation to get the correct values of y? Pause the video now. When you're ready, restart the video to see the solution. The solution to find the regression line for the OR logic is very similar to that of the AND logic. In fact, the only difference in this code is that I changed the output values for y to be the array 1, 1, 1, 0 instead of 1, 0, 0, 0. The name of the data changed as well, but other than that, everything else is the same. We can see that the output gives us an intercept of positive 0.25 with slopes for x1 and x2 of 0.5. As was the case with the AND logic regression predictions, the values provided are not zeros and ones. If we round the values provided here to the nearest integer, we do get the correct solution for our logical operation. Now let's talk about the XOR example. Remember that with XOR, the output will be 1 if the inputs are different, and the output will be 0 if the inputs are the same. As we did with the AND logic and the OR logic examples, we can graph our coordinates and color them by their output value. Note here, though, that there isn't a single line that can be used to partition our data points and accurately categorize them all. We would need to find two different lines to perform that separation, as you see on the screen. This means that linear regression, as we did for the AND logic and OR logic, will not work. To demonstrate this, partial output from the regression analysis of the XOR data has been provided on the screen, along with the model predictions from the best fitting model that Python found. We can see that for this output, each value is listed as 0.5, which means there's no transformation we can provide that will correctly classify each of the individual points. Instead, what we will need to do is come up with linear functions of our input variables with potential transformations on them that provide outputs that could be used to provide this linear separability. For now, I provide these two functions of x1 and x2 on the screen, and I'm calling them h1 and h2. In general, with neural networks, we won't need to find these values on our own. Instead, the software will find the optimal values for us, which is why I won't go into the details of how I selected these two inputs. In the case of this example, we're creating a new value called h1, which must be the sum of x1 and x2. I also produced a new value called h2, which takes on the maximum of 0 and x1 plus x2 minus 1. These are the values I will now graph along with y. Note that only 3 points appear because one of the rows from my new set of coordinates is repeated. This new graph can be separated with a single line, which means we should now be able to use linear regression to find a model prediction. To conduct this analysis, we need to now create a new data dictionary for the XOR. Using the values of h1 and h2 defined on the previous screen, I redefine the data that will be used in this example. I then fit the model and print the summary. Note that only partial output is shown here. Creating predictions from this data, we can see that I get appropriate values for the different rows of my array. While showing these examples gave some practice using the linear regression modeling techniques, the real purpose for this video was to show that not all data are linear separable, and linear models may fail to provide us with accurate predictions in some cases. In fact, most data is not perfectly linear separable, and while linear models will do a reasonably good job in most cases, sometimes we need more complex models that take on multiple layers of the data to provide us with reasonable predictions.